Okay, this is the last section in the textbook, Chapter 12, Section 12.2. Probably going to do about the most math that we've done all year in this section. What we're going to be looking at here in this section is when you collect a set of data and you put it in a scatter plot, what if that scatter plot is not linear? In statistics, we really need the scatter plot to be linear in order for us to be able to obviously run a linear regression and therefore do predictions. So in stats, we always want our scatter plots to look linear. And so we're going to look at this idea of if it's not linear, how can we transform the variables in the data set so that we can achieve a linear or linearity in the scatter plot and then can proceed with a regression and our predictions. And so what this is going to require is for us to achieve the linearity, we are going to need to do some work with logarithms. And so I want to start real quickly here with just a little bit of review on some of the logarithm properties. And then we'll be able to move into how to use these logarithms to transform what looks like a curved data set into something that would look more linear. Okay, so I first just want to review with you how to add logarithms together. If you're going to add two logarithms together, they must have the same base. They also must have a 1 as their coefficient. When you add logarithms together, though, what you actually end up doing with their arguments is you end up multiplying together the two logarithms arguments together. And you can see here my new argument was a 7x, and that was because I took each of the original arguments, the x and the 7, I multiplied those together. Okay, you multiply arguments when you add logarithms together. Okay. Also works the other way. Sometimes you'll have a logarithm like this and you'll be asked to separate it apart into two logarithms. You'll just kind of look at these as two separate factors, break it apart in that way as well. Okay, another property we want to be familiar with here is called the power property. This property essentially says that you can take a power, an exponent, that is on your argument, and you're allowed to pull that down in front. So if we have something like log base 2 of x cubed, we could rewrite it with the 3 as the coefficient. This would be read 3 times log base 2 of x. Okay, this property also works in the opposite direction, that if you have a coefficient in front of your log, you can pull that coefficient up and put it in the exponent on your argument. Okay, we want to be familiar with natural logarithms. Natural logarithms are essentially logs that specifically have a base that is e. Okay, remember, E is a button on your calculator. It's actually underneath the division key. And if you were to press the E button on your calculator, we call that the base E. It is a very specific decimal that keeps going on and on and on here. But there is an abbreviated way that we write a logarithm when the base is E. And we replace the log base E with this symbol, ln, that represents a natural logarithm, and then whatever the argument was that comes after it. So in essence, the log base E is all packaged together in that symbol, ln. Okay, the other thing I just want to make sure that we're familiar with are these exponential and logarithmic inverse properties. Okay, the way these properties essentially work is anytime you have a base number and there happens to be a logarithm in that base number's argument, as long as these two numbers are the same, your base number and the base value in your logarithm that's in the exponent, essentially these cancel one another out, and you are simply left with whatever the argument was in that logarithm. So all of that would simplify down to a y. Okay, so if you have something like 13, and then in the exponent log base 13, whatever this argument is, we'll just say it's a 5, then essentially all that cancels, reduces to a 5. Okay, so what that means is when you see something like a e, and then in the exponent, there's a natural log. Keep in mind what a natural log, an ln, means. That technically means, if we were going to write it out longhand, that means that is a logarithm with a base e. It looks like the argument on this was a y. So here again, we have this situation where these are both the same number. Those are both base e's. So this all cancels, reduces down to whatever the argument was on that logarithm, in this case a y. Okay, finally, we're going to just review real quickly how to solve a logarithmic equation, something like log base 10 of y equals 4. Okay, there's a couple different ways that you can do this, but we want to just really try to apply this property right here, where if our base number has a logarithm in the exponent, and we can show that that base number is the same number as the base on the log, then everything kind of cancels, because after all, what we're trying to do here in this problem is we are trying to solve for that y. So what I'm going to suggest that we do here is we can do anything we want to one side of the equation as long as we do that exact same thing to the other side of the equation. So I'm going to take the left side of the equation, and I'm going to make the left side of the equation actually become the exponent on a 10, so that I'm raising that 10 to the log base 10 of y power. If I'm going to do that on the left side, I must also do the same thing to the right side. I will make the 4 become the exponent on a 10 as well. Okay, the reason I chose 10 is because you can see here now these are both the exact same value, which means this would cancel, leaving me with just a y. Y would equal 10 to the 4th, or in other words, y would equal the number 10,000. Okay, that is a very brief review on logarithms, but some of those little pieces are going to come into play with some of the problems that we're going to be doing today. And so you have this kind of little snapshot here, this review of logarithms here that we can kind of reference. Okay. After today's lesson, you should be able to do these few multiple choice questions from the previous section, as well as these problems right here. One thing worth noting on your homework, please just make all the scatter plots on your calculator. Even if it mentions to make it by hand, you can make all the scatter plots on your calculator. This is going to be great review from chapter 3. If it asks you to describe the scatter plot, you're going to use that DUFS acronym from chapter 3 to describe the scatter plots, giving the direction, unusual values, form, and the strength. Okay, so one thing that we want to just talk about here in this the first part of this section is what linear regression allows us to do is it allows us to find a line of best fit, and then we can perform inferences about the slope of the line of best fit. But the issue is, what if the data is not in fact linear? Okay, the data must be linear in order for us to run a linear regression and then, of course, perform these inferences on the slope. So one powerful technique that we can use to handle data that is actually not linear is we can perform transformations on either one or both of the variables, and that can actually make the scatter plot then appear linear. Okay, remember, transformations are really just, doing some operation to your variable. Okay. Now, here in its most general sense is how a linear model would look. It takes on the form variable equals constant plus constant times variable. Now, I want to break that down for you here real quick, because I know that we are most used to thinking of a linear model in the form, at least in stats, we use the A as our y-intercept, and we've been using the b actually as our slope. So variable, this would be what we would call in stats our response variable. That's our y. Okay, our y variable is our response variable. The constant here, in this case, that would be our y-intercept is a constant. Then it has over here plus constant. Well, that would be the slope. It's the coefficient in front of the x. And then finally, another variable here, the x, we refer to that in statistics as our explanatory variable. The explanatory variable x is what we use to try to make predictions about the response variable y. Okay, but this is the general format here. This is what we're going to be keeping coming back to here. Variable equals constant plus constant times variable. This generically is how all linear models look. And so what we're going to be focusing on here today is we're going to be looking at what if the initial scatter plot is either a power model or an exponential model. Okay, we know both of these things are curves. Now, when we talk about a power model, I want you to pay attention to where you see like the A's, the B's, the P's. Those are constants. Okay, those are constants. So I'm just going to give you a quick example. Here would be a power model. I'm just going to plug a constant in for the A. I'll plug in another constant here for the P. Anything like 2x cubed, something x squared, just any exponent on the x other than a 1, that would be considered to be a power model. We know there are curves to those. Okay, so those are not linear. Okay, over here, exponential, this is when your variable is actually up in the exponent, and what you see as the a and the b, those would have constants. Okay, we know an example of that might look something like this, 2 times 4 to the x power. Okay, we know that exponential growth has a curve like that. Exponential decay, the curve then goes down that way. Okay, so the idea here is our scatter plots are either going to start out either being a power model or they're going to be an exponential model, and we need to come up with a way to transform the data set so that we can try to make the data set linear. Okay, and what we're going to use here is we are going to use logarithms. Logarithms are useful to help us achieve linearity when the relationship between the two variables is either a power model relationship or an exponential model relationship. Okay, so what we're going to focus on here first is we're going to focus on a power model. What if the original scatter plot is more in this format here? Okay, so if the scatter plot is a power model between our two variables, then we can get a scatter plot of logarithms of both the variables is going to make it look linear. Okay, let me rephrase that here. We can get a scatter plot that looks linear if we transform the data set by taking the logarithm of both the explanatory variable and the response variable. Okay. Now, you can do this with a common logarithm, log base 10, or you can do it with a natural logarithm. So you can either take log, and I'm going to insert the word or here, or you can take a natural log of both of your variables. Okay. So you would either plot natural log of x, natural log of y, or log x, log y, either one. Okay. When you transform every x variable into, say, log x and every y part of your point into log y and plot those new points, that is going to create a linear plot. Okay, a linear plot. And if it actually does if the scatter plot looks linear, that means the original model was a power model. Okay, now I want to show you why this works. So I'm just going to kind of talk you through sort of the basics here of what happens here, why a power function relates to a logarithm here. So if you could just follow these few steps here that I have off to the side, 1, 2, 3. Okay, you can see what we're starting out here with is a generic version for a power model. Remember the P as well as the A, those are constants. We're going to keep those in mind. Those are constants in this problem. Okay, so what we're going to suggest that we do here is we're just going to take the logarithm of both sides of this equation. So I'm just going to do a common logarithm here. I'm going to do log of y. So I did that on the left. So on the right, I'm going to do log of ax to the p. So ax to the p is the argument of that logarithm. Okay, then it suggests here in step 2, we're going to use logarithm properties. We're going to separate this logarithm over here on the right side into 2 separate logarithms. Okay, now remember, I think we talked about when you combine and add 2 logarithms together, you actually multiply their arguments. So I want you to think of these 2 things, a and x to the p, as maybe the 2 original arguments of 2 logarithms, and I'm going to separate this. I'm going to leave log base y on the left, but I'm going to separate this into log base a plus log of a plus log x to the p. Okay, the assumption here is the bases on all these logs are 10s if you don't see a base there. Okay, so I'm going to doing kind of the reverse of combining logs together and breaking this apart into 2 logarithms. That's what this meant by separate into 2 logs. Okay, and then we're going to put it in the form of a linear function. Now remember, a linear function generically takes on this format. Okay, we want a variable on the left side equals a constant plus a constant times a variable. Now, one last thing I want to do to this here is I'm going to grab this p that's in the exponent, and according to that power property that we reviewed on that opening slide here, we're allowed to pull that exponent on our argument down in front of that logarithm, which would then make it look like this. Okay, so let's see if we have achieved linearity here. We're supposed to have a variable on the left side. Okay, I have a y here. That is my response variable. So log base 10 of y represents a variable. Then I'm supposed to, on the other side of the equal sign, have a constant. Now, remember, the a, it represents a constant. So if you had log and then you had a number there, that actually represents a constant value, okay, because a is a constant. Okay, then plus, supposed to have a constant. This is like the slope, okay. The p right here is a constant. Okay, we were told that again in the original problem here. Remember, this p was a constant. And then finally, the variable would be this logarithm base 10 of x represents a variable. Okay, so basically what we did here is you can see what we have is we have log of our explanatory variable and log of our response variable. When we did that here, this achieved this kind of linear format. Okay, this is just kind of explaining why. We'll get into the examples so that you'll see sort of what it is that you're going to need to do for these problems. Let's take a look at this fishing example here. Okay, it says, imagine that you've been put in charge of organizing a fishing tournament in which prizes will be given for the heaviest Atlantic Ocean rockfish caught. You know that many of the fish caught during the tournament will be measured and released. You're also aware that using delicate scales to try to weigh a fish that's flopping around in a moving boat will probably not yield very accurate results. It would be much easier to simply measure the length of the fish while you're on the boat. But what we need some way to be able to convert the length of a fish into its weight. Okay? That's what we're after here. And so you contact the nearby Marine Research Laboratory, and they provide reference data on the length in centimeters and weight in grams for Atlantic Ocean rockfish of several sizes. So what you see here is we have a bunch of data. These are the lengths in centimeters of different rockfish, and these are the weights in grams of those particular fish. And so what that creates here is that creates essentially this scatter plot that you see right over here. Okay, this is the original set of data. And you can tell by looking at it, it does not look linear. There is a distinct curve. Now, it's really hard to tell on some of these scatter plots whether the initial curve is exponential or whether it's more of a power model. Okay, and we're going to talk through sort of how to distinguish that. But what I want you to focus on here right now is that our explanatory variable is the length. We'll be using that to make a prediction about the response variable, which is the weight. The issue is I should not be running a linear regression with this original set of data, this set of data that I would have over here, okay, because that is not creating a linear model at all. Okay, so what we're going to do is we're going to transform this data. Okay, if you notice what we have in this next scatter plot here, we have our explanatory variable, instead of being length, is now log base 10 of the length, and our response variable, instead of being the weight, is now log base 10 of the weight. So essentially, how we got these points here is we did log 5.2 as our new x value and log 2 as our new y value. We plotted that point. We did log of each of these and plotted those new graphs. Okay. If we were to run a linear regression with this transformed set of data, and then look at the residual plot that's formed over here. Remember, a residual plot, if it feels relatively scattered above and below with no distinct pattern or evident pattern, that means that a linear regression would be appropriate for that data set. Okay, this feels pretty scattered. There's no evident pattern here per se, so I'm feeling pretty good about this transformation we did and that we're achieving linearity here. Okay, so let's go ahead then and take a look underneath this. You see a computer output that is ran on not the original set of data. Notice that our explanatory variable is log of the weight, and that's our response variable, log of the weight, and our explanatory variable is log of the length. Okay. All right, so here's our first question here. In part A, it says, based on the output, explain why it would be reasonable to use a power model to describe the relationship between weight and length for Atlantic Ocean rockfish. So basically, you're backing into these problems. It's really hard to tell when you look at this original set of data, if this original set of data was exponential in nature or a power model. What you can tell is once you transform the data, and I know right now we're only talking about power models, but if you transform the data by doing log of your explanatory variable and log of your response variable, and that achieves linearity, that means that the original scatter plot was in fact a power model. So what we're going to say is it is reasonable to use a power model because the graph of log length, comma, log weight, this is my transformation, has a linear form. Okay. I'm also just going to make the comment that the residual plot of the transformed data shows no evident pattern. Okay, also. Okay, just make that additional note there. Okay, so what we're asked to do here in part B is we're asked to give the equation of the least squares regression line. We want to make sure that we're defining any of the variables that we're using. Okay, now remember how this works? When we're looking at our computer output, this second row here in the coefficient column, that represents our slope. And in the first row, in the constant column, this represents the y-intercept. Now, make sure that you're careful. We need to be using the transformed x and y variables. So it's log with an argument of weight. Okay, and I'm going to put a big hat over top of that. That's the predicted log weight. Okay, would equal, I'm going to put my y-intercept, that's the negative 1.89940, plus, I fill in my slope here. And I'm going to go ahead and put as my explanatory variable, it's not length, it's log of length. Okay, length is the argument there. Okay, so then we're using that equation to do this next part here. Suppose that a contestant in the fishing tournament catches an Atlantic Ocean rockfish. And again, remember, we're not going to weigh them on the boat because it's too rocky, the scales are too delicate. We're going to measure the length of that rockfish, and it's 36 centimeters long. We want to use this model right here that we discovered in part B to kind of make a prediction about what we think that fish's weight would be. Okay, so we know how long it is. So I'm going to be substituting into our formula here 36 centimeters for the length. Okay, this will be log 36. Okay, if we type all this into the calculator, and that would just be the LOG button to the left of the 7, because that's a common logarithm here, the number that you're going to get on the right side is 2.8404. Okay, now remember, we need to actually get this equation solved for weight. I really don't want this logarithm in front of it. I want just the predicted weight to be here. So for me to cancel this off, and keep in mind, I'm going to go ahead and put it here, the base of this logarithm is a 10. So I'm going to go ahead and raise this left side 10 to the log base 10 of weight. And I have to do the same thing here to the right side. That's that property that we reviewed, that since these are the same, we can cancel that out. This is going to leave me with, okay, here's the predicted weight would be whatever 10 to the 2.8404 would be, and that is 702.1, and this would be grams. Okay, so you have to use a little bit of math there to solve that. All right, so here's what we're after here, an important thing. Important thing to remember is that if the relationship between the two variables is described as a power model, okay, now we weren't told that it was a power model. We really were able to know that after we transformed the data. If it's actually a power model, then it will become linear after you take the logarithm of both the explanatory and the response variables. Okay, so you do the transformation, you take log of the x variable, log of the y variable, and then if the scatter plot looks linear, then you know, okay, that original curve was in fact a power model. Okay, let's take a look at an exponential model here real quick, okay? If an exponential model, here's the form for exponential models right here, okay? If that describes the relationship between x and y, then we can use logarithms to transform the data set again into a linear relationship, okay? All right. Okay, so once again, sometimes the scatter plot, rather than being a power model, can be an exponential model. Again, this is difficult for you to tell by just looking at the scatter plot, but if it is exponential, we can transform the data by turning it into a linear relationship. I'm just going to show you sort of how this works here. We start out with an exponential function. Once again, just a reminder that the a and the b are both the constants, and notice that the variable x, the explanatory variable, is in the exponent when we're talking about an exponential function. Okay, we're going to follow these 3 steps just so you can kind of see how the transformation happens. We're going to take the logarithm of both sides of the equation, so log y, and then on this side, log of ab to the x. Okay, we're then in step 2, we're going to use the logarithm properties to separate the logarithm on the right side into 2 logarithms, okay, similar to what we did when we were doing this with the power function. So I'm going to split this into log base 10 of a plus log base 10 of b to the x. And then we're going to use that power property where we're going to pull this exponent of an x down in front so that we have on the right side log a plus x times log b. Okay, now, once again, just a refresher here, this is the generic form of how all linear equations look. We should have a variable on the left side. That's what we have here with a log of y. That represents our variable. Okay, a log of a constant, the a is a constant. This represents then what would be a constant value. Now, you see here, this is constant times a variable. This x right here is our variable. And this log b, remember b is a constant, represents the constant. So those are just kind of flip-flopped. Here it's expressed variable times constant, and these are flip-flopped here. But you can see that essentially what we have here is we have that generic form for a linear function. Now, what I want to draw your attention to here, though, is notice in this linear function, we took log of our response variable, but there's not a logarithm in front of our explanatory variable. And so if the original data set is exponential in nature, the transformation is going to be to leave the explanatory variable exactly the same. We don't transform that at all. And we only transform the response variable by taking the log of the response variable. So let's look at this example, and then we'll be able to see in the next video sort of how all of this ties together. This is talking about Gordon Moore. He's one of the founders of the Intel Corporation, and it was predicted in 1965 that the number of transistors on an integrated circuit chip would double every 18 months. This is called Moore's Law, and it's one way to measure the revolution in computing. Here are data on the dates and number of transistors for Intel microprocessors. Okay, so we have these dates here. We have the number of transistors. They're saying that it's supposed to double every 18 months, which does kind of allude to an exponential function. But anyhow, what we have over here, this graph, we'll go ahead and label that this represents the original scatter plot. Okay, the original scatter plot. Now, notice that the x variable, the explanatory variable, is not actually the year, but it is the number of years since the year 1970, and our response variable is the number of transistors. Okay, you clearly can tell in this scatter plot there's definitely a distinct curve and a pattern happening. It would be a very poor decision to try to run a linear regression with this set of data. Okay, we need to transform the set of data so that it achieves linearity and then run the regression on the transformed set of data. And so to transform this data, what we're going to do is we're actually going to leave the explanatory variable the same. Okay, notice we're not changing the x-axis at all. We're going to keep the explanatory variable the same, but we are going to transform the response variable. In this case, I'm doing natural log of the y variable. You could just as easily do log of the y variable. Okay, so let's see how this shakes out here. You can see that in this particular scatter plot of the transformed data, now this definitely looks much more linear. Maybe a little slight curve here at the end, but definitely feels like this is much more linear. When the original set of data is exponential in nature, when you leave the explanatory variable the same and transform the response variable, if the result is relatively linear, that means the original data set was in fact exponential. So here we see in part A, it says a scatter plot of the natural logarithm of your number of transistors on a computer chip versus the years since 1970 is shown. Based on this graph, explain why it would be reasonable to use an exponential model to describe the relationship between the number of transistors and the years since 1970. So essentially, what this question is asking is, what was this original model? Was this exponential or was this a power model? Well, after we performed this transformation, we can say that it's actually reasonable to use an exponential model, okay, meaning that's what the original data set was, an exponential model. Okay, it's reasonable to use that because the graph of, Okay, now I'm kind of citing here, this is what the transformed data is. My explanatory stayed the years since 1970. My response variable was the natural log of the number of transistors. That was my response variable. Has roughly a linear form. We don't have the residual plot to look at for this particular problem, but I can definitely conclude that that original data set was likely an exponential model because when we performed this particular transformation, it appeared roughly linear. Okay, so on the next page here, I think I might have this backwards here. This is what we want on our next page here. This is what you should be seeing. The mini-tab output from a linear regression analysis on the transformed data is shown below. Okay, give the equation of the least squares regression line and be sure to define any variables. So here's what I want to write out first. Here's what our transformation was. The x variables stayed the same. The y variables, we transformed those by taking the natural log of the y variable, which was the number of transistors. Okay, remember this row right here, this represents our slope, and this constant row represents our y-intercept. So our new response variable is natural log of the transistors. I'm going to put the hat symbol on that, equals our y-intercept plus our slope times our explanatory variable. And we want to make sure that we're defining all of our variables. So I'm going to draw a little arrow here and say that the x is the number of years since 1970. Okay, now in part C, it says use your model from part B. So we want to use that equation that we just wrote down to predict the number of transistors on an Intel computer chip in the year 2020. And we want to show our work. Okay, so we're going to use our equation here. And our goal is to solve this for the transistors variable. 2020 is the year. Now remember, we need to substitute in how many years 2020 would be since the year 1970. That would be 50 years later. Okay, we type all the numbers on the right side into our calculator, and we get 25.3562. On the left side, we have natural log of the number of transistors. Okay, and once again, there's a hat symbol over top of that. Now keep in mind, the goal here, we need to get just transistors by itself. We need this natural log to cancel. Okay, remember what the base is on a natural log. The base is an e. So if I were to raise this entire left side, e to that power, and do the same thing to the right side, that would in effect cancel out my natural log, leaving me with just the predicted number of transistors equal to whatever e to the 25.3562 power would be. Okay, that comes out if we type that in. It's a really big number. It's expressed in scientific notation. It's, roughly about 100 billion transistors is what would be predicted for the year 2020. Okay, I want you to look at part D here real quick. We're almost done with this video. A residual plot for the linear regression in part B is shown below. We see this off to the side here. Discuss what this graph tells you about the appropriateness of this model. Now, I do want to point something out. Normally, when you're looking at these residual plots, you're looking to see if there's any evident pattern. It does kind of feel like there is a little bit of sort of an ebb and flow to this pattern somewhat here. Okay. Now, I will say that when we looked back at, on the previous page here, when we looked at after we ran the, or created the scatter plot from the transformed data, this definitely looked much more linear than the original set of data. Now, we are seeing somewhat of a pattern here in the residual plot, but we're going to say for part D, anyhow, that the residual plot shows a slight pattern. However, the transformed scatter plot is much more linear than the original scatter plot. So we can be, we'll say, reasonably comfortable with our predictions. Okay. So we probably have a reason to have a little bit of caution because of what we're seeing in that residual plot, but we can be somewhat comfortable because the transformed scatter plot does look somewhat linear. Okay, and the last thing here that we're just going to touch on very, very briefly is I think that a crucial property of these logarithms for our purposes is that if a variable is growing exponentially, then its logarithm is growing linearly. Okay, once again, I'm going to ask here that on your homework, you can just do all the scatter plots on your calculator, and when you're asked to describe those, you're going to use the Duff's acronym from Chapter 3. Okay, and here are some problems that you can go ahead and try that go along with this video.